welcome to the very first official episode of the Pea PodCast. Brr, 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 brr. Shh, shh. For our very first episode, I wanted to lay a foundational stone for everything we'll discuss going forward. Because often when we hear about a new health claim, it's prefaced with, a new study shows. But what does that actually mean? How do we know how to evaluate if that study is worth its salt? Today, we're going to demystify scientific research, specifically clinical studies, so you can become a savvier consumer of health information. Think of it as your crash course in understanding how we know what we know about health. Let's start with a big one. How much does it matter how many people are in a study? This is what we call a sample size. Imagine you want to know if a new vitamin helps people sleep better. If you test it on just two of your friends and one says yes and one says no, that doesn't really tell you much, does it? It's just what we call anecdotal. Now, if you test it on 200 people and 150 of them report sleeping better, that's starting to look a little bit more convincing. Generally speaking, the larger the sample size, the more reliable the results. A larger sample size reduces the chance that the results are due to a random chance or individual variations. It allows researchers to capture a more representative picture of the larger population that they're trying to understand. However, simply having a large sample size isn't enough on its own. It's just one small piece of the puzzle. Next up, let's talk about the different types of study designs and why they matter. This is crucial because the type of study dictates what kind of conclusions we can draw from it. At the top of the hierarchy for determining cause and effect, we have randomized controlled trials. We also call them RCTs when we don't feel like saying the whole long thing. These are often considered the gold standard in clinical research. Here's how they generally work. Participants are randomly assigned to one of two groups. One group is called the intervention group, and that group receives the treatment or the intervention being studied, like a new medication or a new diet. The other group is the control group, and they receive either a placebo, which is a sugar pill, for example, or just standard of care, whatever that means for that situation. So maybe just continuing to eat the way they've been eating instead of the intervention diet. It helps to ensure that groups are as similar as possible at the start of the study. So any differences in outcomes can be attributed to the intervention and not to other factors. We call those confounding factors. If a study is well designed and conducted, an RCT can provide strong evidence for a cause and effect relationship, meaning that we can say that X caused Y. Below RCTs, we have some other important study designs. The first step is an observational study. These studies observe people and collect data without intervening or assigning treatments. Next up, there's cohort studies. This is where researchers follow a group of people over time, observing who develops a certain outcome, like a disease, and who doesn't, and looking for their exposure, i.e. their diet and lifestyle. For example, following a group of smokers and non-smokers over 20 years to see who develops lung cancer. These can show an association, that is, that X is related to Y, but not necessarily a cause and effect. So they can't prove that X caused Y. Then there are case control studies. These studies work backwards. Researchers identify people with a specific outcome, the cases, and compare them to a similar group without that outcome. Those are the controls, to see if there's a difference in past exposure. For instance, comparing the past dietary habits of people with heart disease to those without. Again, these show associations, but cause and effect is harder to prove. Next up, there's cross-sectional studies. These are like a snapshot in time. Researchers collect data on a group of people at a single point in time to see the prevalence of a condition or exposure. For example, surveying a group of adults about their current exercise habits and anxiety levels. These are good for understanding the prevalence, but offer limited insight into cause and effect. And now for my personal favorite of all the study designs. Yes, I'm a nerd who has a personal favorite of all the study designs. And these are the ones that you'll find me reading most often on my own. And that's systematic reviews and meta-analyses. These aren't individual studies, but rather powerful analysis of many existing studies. A systematic review rigorously gathers and summarizes all the relevant research on a specific question. A meta analysis takes it a step further by statistically combining the results of multiple studies to provide an even more robust conclusion. These are often considered the highest level of evidence because they draw on a larger body of data. So, what do these different designs, or why do these different designs matter? Because the strength of the evidence changes drastically. If you read a headline based on a cross-sectional study suggesting a link between coffee and happiness, that's interesting, but it doesn't mean coffee causes happiness. It could be that happier people just tend to drink more coffee. And RCT, however, could be designed to test if coffee improves one's mood. Always look for the study design when evaluating a health claim. And don't worry if you don't, because this podcast's whole aim is to look at the study design for you and tell you exactly what it means. And if this is all way too confusing, don't worry. We'll continue to break it down every episode. We'll do all the heavy lifting for you. Now, let's tackle a term that sounds intimidating, but is really quite important: statistical significance. And I'm going to warn you, if I say statistical significance too many times, my brain starts to combine the words. So let's see how far I get talking about statistical significance before my brain melts. Already it's fizzling. When a study says its results are statistically significant, it doesn't mean that the results are necessarily more important or meaningful in a practical sense. It means that the observed difference or relationship is unlikely to have occurred by a random chance. Imagine you're testing a new medication and the group receiving the drug shows a small improvement over the placebo group. I knew I'd do it. Statistical significance helps us determine if that small improvement is a real effect of the drug or just a fluke, something that happened more randomly. Researchers typically use a p-value to determine statistical significance. Without getting too technical, because this can get really down in the weeds, a p-value less than 0.05, often written as p with that like less than symbol 0.05, is generally considered statistically significant. This means there's less than a 5% chance that the observed result happened by random chance if there was truly no effect. So why does this matter? Because it helps us weed out random noise from actual signals. However, it's crucial to remember that statistical significance doesn't always equal clinical significance. A tiny improvement that is statistically significant might not be big enough to make a real difference in someone's life, although the math looks good. We need both statistical significance and practical importance. Whew, I made it, y'all. Now, let's talk about the weight of the evidence. Here's a big one. Is one study alone enough to change medical recommendations? Well, the short answer is almost always a resounding no. This is why I love a systemic review and meta-analysis so much, because it's not just one study. But think of scientific research as building a wall, brick by brick. Each well-designed study is a single brick. One brick, no matter how perfectly crafted, cannot hold up a roof. You need many bricks laid systematically. Y'all, this systematically is going to kill me to build a strong, reliable structure. Medical recommendations, especially from reputable organizations, are rarely based on a single study. They are typically based on a large body of evidence that has accumulated over time, reviewed by experts, and then synthesized into systematic reviews and meta-analyses. When multiple studies, ideally of strong design like a randomly controlled trial, consistently show the same result, that's when we start to feel confident in making broad recommendations. So when you hear about a new study, it's exciting, but it's just one piece of the puzzle. It opens up new avenues of research, but it usually doesn't rewrite the rule book overnight or even over a decade. Unfortunately, a lot of headlines are of a single study that has little to no additional evidence. And those headlines don't tell us anything else truly about that study. That's what ultimately makes a compelling headline. You won't see a headline that reads, "Vegetables are good for you," because we already know that. So that article won't get that many clicks. News outlets won't pick it up, and it definitely isn't going viral. But if you say, "Eating broccoli every day may cure your breast cancer," well, now you've created an enticing headline that would even lure me in to see what it's all about. Finally, let's talk about something often overlooked but incredibly important. How much does it matter who funded the study? Well, it matters a whole heck of a lot. Research can be crazy expensive. Studies require funding for equipment, personnel, participant compensation, and so much more. This funding can come from various sources: government grants like the National Institutes of Health in the US, charitable foundations, academic institutions, and importantly, private industry, much like the pharmaceutical company or food manufacturers. While not all industry-funded research is inherently biased, it's crucial to be aware of potential conflicts of interest. A company funding research on its own product might have a vested interest in seeing positive results. This doesn't automatically invalidate the research, but it does mean we should really scrutinize it even more carefully. Reputable scientific journals often require researchers to disclose their funding sources. So, when you're looking at a study or an article about a study, try to find out who funded it. It's usually either on the very first page or very down below on the very last page. And ask yourself once you find that funder, does the funder have a financial stake in the outcome? The awareness can help you critically evaluate the findings. Transparency is key. So, to recap our crash course in scientific research: 1. The sample size. Bigger is generally better, but it's not the only factor. The second thing we looked at is the study design. Remember, randomized controlled trials are king for cause and effect, but observational studies can show important associations. Know the hierarchy of the evidence and follow it. The third thing we touched on was statistical significance. Look, I said it. That means the result is unlikely due to chance, but it doesn't necessarily mean that it's practically important or clinically relevant. The fourth thing we talked about was the body of evidence. One study is rarely enough to change a recommendation. Look for consistent findings across multiple, well-designed studies. Remember, those meta-analyses are so important as they already draw together all or most of the available research on a topic. And lastly, funding. Be aware of the potential conflicts of interest when studies are funded by an industry. This might seem like a whole lot to take in, but my hope is that this episode gives you a basic toolkit for understanding the foundations of health claims. Next time you see a headline about a new study, I encourage you to pause and ask yourself these questions. Who is in this study? How is it designed? Is this one study or part of a larger body of evidence? And who paid for this? By asking these questions, you'll be well on your way to becoming a more informed and empowered participant in your own health. If you're a big old science nerd and want to dig deeper into the information we discussed today, all the references and resources are linked in the show notes for this episode. Just tap the link in your podcast app. To make sure you never missed a single pea-sized nugget of wisdom, be sure to like and subscribe wherever you're listening right now. And if you enjoyed what you heard, we'd absolutely love for you to leave us a comment or review. It really helps new listeners find us. Want to keep the conversation going? You can find the Pea Podcast every single day on social media. Connect with us on Instagram, Facebook, and Threads by searching for Pea Nutrition. And if you'd like to follow my personal journey and insights, you can find me, Alicia Simpson, as the ADHD Nutritionist on TikTok, Instagram, and Threads. If you have a headline you would like us to dive into and feature on the Pea Podcast, email us at podcast@peapodnutrition.org. That's podcast@peapodnutrition.org. Thank you so much for joining me today. Until the next time, stay curious, stay critical, and keep nourishing your body and mind. See you soon.